Hello everyone, I am Aswani, Assistant Professor, Department of CSE AIML at MLR Institute of Technology. Welcome back another session of Artificial Intelligence. In this today's session, we will see what is pooling, what is padding, and the layers to build the convnets, convolutional neural networks. Okay, let's see the overview. So here we'll see the padding, pooling, example, how to apply the padding, how to apply the pooling, and what are the layers to build the convolutional neural networks. Okay, so let's see the pooling. So why we use the pooling? In the previous sessions also we have discussed what is pooling, what is padding, and what is the input layer, what is the convolutional layer, what is the activation layer. All those things already we have seen in the previous sessions. In this session, in the pooling and padding, we'll see the example, and also in the what are the layers to build the convnets also we will see. Okay, let's see the pooling. So pooling is used to downsampling operation, which is used to reduce the dimensionality of each feature map. So whatever it will complete the task from the convolution layer, it will take that feature map from that previous layer and it will apply the pooling layer. Why? Because the feature map is from huge size, then it needs to be reduced. Why? Because if you apply the pooling, it will be reduced the size of feature map and it is easy to train that model. In that scenario, we need to apply the pooling. Okay, so there are different types of pooling: max pooling, average pooling, and global pooling. Let's see the max pooling. Max pooling selects the maximum value from each region of the feature map. For example, consider this is the feature map. Then, for example, if a 2x2 pooling window, then 2x2 or 3x3, based upon the feature map, it will take the size of that pooling. So here we have taken 2x2. So this is the one of the layer, and this is the one of the pooling, and this is the another one, and this is another one. So from this, the max pooling means it will apply the max pooling. From this 2x2 window, it will take the maximum value, that is called max pooling. So selects a maximum value from each region of the feature map. So out of this feature map, we'll get only 2x2 because only 4 regions we are getting. So here from the first region, which value is the highest one? 9. In the second region, 7. After that, third region, 8. And last one, 6. 9, 7, 8, 6. After applying the pooling, this is the output. So the pooling is used to reduce the dimensionality of each feature map, but retains the most critical information. The convolution layer also used to extract the important things, means edges, curves, patterns. But in the pooling, maximum it will extract the remains the only critical information. Whatever important from that image, it will retains only that information. Okay. Next, average pooling. It will also take the same 2x2 pooling, but here it will perform the average. Let's see. Computes the average value of each region like a max pooling. A 2x2 window averages the value of each 2x2 block. First, it will take 2 plus 2 plus 9 plus 4 divided by 4. So the output is 4.25, and again from for this block 4.25, and again this block 4.25, and again this block 3.5. In such a way, it will take the average pooling. Okay, it will perform average operation. Next one, global pooling, which means it will apply to entire feature map. In this global pooling, again we will have max pooling and another one is average pooling. So in the max global pooling, it will take out of entire feature map which value is maximum. It will consider only that value. Okay. In the next average global pooling, it will take the average of entire feature map. The entire feature map it will be taken as the consideration. Let's see global pooling. Applies pooling across the entire feature map, producing a single value for feature map. Let's look at this one, average pooling. So out of this entire feature map, we have the output as 2x2. Okay, but when you consider global pooling as an operation, it will it will produce only one value as the output. Applies pooling across the entire feature map, that is the first point, producing a single value for feature map. This is often used at the end of the convolution layers before fully connected layers. So maximum in all the scenarios, it will consider the max pooling maximum time, so it will be used. Okay. So the pooling layer typically have parameters such as pool size, the size of window 2 by 2 or 3 by 3, depends on the feature map. Next stride maximum, it is 2. The step size with which the window moves across the input, maximum it will be 2. The next one, padding. The padding involves adding extra pixels around the border of the input to control spatial dimensions of the output. So, for example, if you take any feature map, then it will have the less critical information only. If you want to return the previous layer's size, or the original image size returns the same, then we will use the padding. To add the extra information, we will add the zeros to the already existed feature map. Okay, let's see. Size prevention. Why we use the padding means, here the first one is size preservation, the second one is border information. So how we will preserve this one? By adding the extra zeros, padding. Without padding, the size of the feature maps decreases after each convolution layer. In the previous, we have seen in this pooling, this is the first feature map. After performing pooling, only 2 by 2 as the output. So it will decreases the size of the feature map. To retain the original size of that feature map, we are applying the padding. So why we need to apply? The first one is size preservation, second one is border information. In size preservation, without padding, the size of feature maps decrease after each convolution layer. Padding allows the spatial dimension to remain constant. So whatever feature map is there, it will add the zeros to entire the border to that feature map. Like this, it will add the zeros. Next, border information ensures that convolution operation consider the edges and corners of the input data. Whatever feature map is there, it will add the two borders, it will add the extra padding values. Okay, so there are different types of padding. The first one is valid padding. So in this valid padding, only applies the convolution where the filter fully fits inside the input, resulting in smaller output dimensions. So no padding, it won't add any values. That is valid padding. Next, same padding. So here add zeros, it will add the zeros. For example, this is the input image. After applying padding, we can look the image look like this. So in the borders from horizontal, vertical, it will add the zeros to entire image. Same padding. Adds zeros around the input to ensure output has the same dimension as the input. So there is no changes. After applying the padding also, the size of the image retains the same. The amount of padding needed to maintain spatial dimensions can be calculated using P equal to K minus 1 divided by 2 is the formula. K is the kernel value, minus 1 divided by 2 is the formula for calculating padding. Let's see the applications. So already we have seen the CNN application. The same applications here also will be there. Image recognition. CNNs with the pooling and padding are widely used for image classification task, whether it is a cat or a sparrow, like that. Object detection helps in localizing objects within the images. For example, in the traffic signal, it will draw the images. Next, medical imaging. It will assist in detecting anomalies in medical scans. Abnormalities it will find. Using pooling and padding are fundamental techniques that enable CNNs to learn and recognize the patterns in visual data. Okay. In the next, we'll see layers used to build convnets, convolutional neural networks. So in this convolution neural networks, already in the previous sessions we have seen what are the different types of layers. We'll see in once again, and how it will be performed layer by layer also we'll see. The first one, input layer, that is the raw image we will given this to the convolution layer. Input layer, convolution layer. This convolution layer extract the image of edges, curves and patterns. Next, after convolution layer, it will apply the max pooling. Whatever from the feature map, from the output of the convolution layer, it will apply the max pooling and it will take the maximum value to each region. Next, dense layer are fully connected layer. After completion of this max pooling layer, it will comes to the fully connected layer. Then it will connect each region to one neuron to another, and it will identify the image. Next, last one, output layer. This one is the judgment layer or prediction layer. It will classify, so okay, this one is a cat, this one is a sparrow, like that. It will categorize the images. So the convolution layer applies filters to input image to extract features. The pooling layer downsamples the image to reduce computation, and fully connected layer makes the final prediction. The networks learns the optimal filters through backpropagation and gradient descent and general method. Okay, what are the layers? So here already we have seen that image input layer, convolution layer, and max pooling layer, dense layer and output layer. We'll see one by one. Okay, here in this example we have taken as a data set, that is a 32 by 32 by 3. This is the height and width of that image, and 3 is the channel, that is RGB. If it is a grayscale image, then the value here is 1. The first one, input layer. So it will, in the input layer, it will take the raw image. It's the layer in which we give input to our model. In CNN, generally the input will be the square sequence of images. This layer holds the raw input of the image with width 32, height 32 and depth or channel or colors is 3. So in the input layer, it will take the raw image of the sizes, width, height and depth. Next, convolution layer. This is the important layer, and here it will apply the in this convolution layer, it will extract all the important features of that image. Okay, let's see. This is the layer which is used to extract the features from the input data set. It applies a set of learnable filters known as kernels to the input images. The kernels are nothing but smaller matrices, usually 2 by 2, 3 by 3 or 5 by 5 shape based upon the image. It slides over the input image data and compute the dot product between kernel weight and the corresponding input image patch. For example, this is the image matrix, and will take 2 by 2, 3 by 3 or 5 by 5 kernel. This kernel will slides over our entire image and it will extract the features from this image. The output of this layer is referred as feature map. Whatever output will come, that is called as feature map. Suppose we use a total of 12 filters, means from entire this image, this kernel is slides over 12 filters. For this layer, we will get an output volume of dimension 32 by 32 by 12 is the output. The next layer is activation layer. In this activation layer, the size retains the same. It will apply the activation function based upon that scenario. By adding an activation function to the output of the preceding layer, that is nothing but convolution layer, activation layers add non-linearity to the network, whatever which is identifying the patterns, those edges, shapes. It will add the non-linearity to the network. It will apply an element-wise activation function to the output of the convolution layer. Some common activation functions are rectified linear unit, max of 0, x is the formula, and tan h are leaky ReLU. The volume remains unchanged, hence output volume will have same dimensions as previous layer contains, that is 32 by 32 by 12. The next layer is pooling layer. Already we have discussed in this session only. In this pooling layer, it considers the max pool maximum. If it is a 32 by 32 by 12, the output is 16 by 16 by 12, because it will take the half of the next out. It will take the total image into the half as the output. Let's see. This layer is periodically insert the convnets, and its main function is to reduce the size of volume, which makes the computation fast, reduces the memory, and also prevents overfitting. Two common types are max pooling and average pooling. We use the max pooling 2 by 2 filters, and stride is usually 2. The resultant volume will be 16 by 16, because the previous layer size is 32 by 32. Exactly half is 16 by 16. Let's see. Single depth slice. The max pool is the first one 6, the second region 8, third one 3, fourth one 4. Max pool with the 2 by 2 filter, and stride is 2. The next one is flattening. The resulting feature maps are flattened into a one-dimensional vector after the convolution and pooling layers, so they can be passed into a completely linked for a categorization or regression, whether it is a cat or it is a dog. Next one is fully connected layer. It takes input from previous layer and computes a final classification. The output layer. Output from the fully connected layer is then fed into the logistic function for classification task, like a sigmoid or softmax, which converts the output of each class into probability score of each class. This is the output layer. It will give the categorization or regression. Let's see the disadvantages of CNN. Computationally expensive to train the a lot of memory is required. Can be prone to overfitting. If not enough data, proper regularization, then it is prone as a overfitting. Requires a large amount of label data. Interpretability is limited. It's hard to understand when the network has learned. Okay, let's see advantages of CNN. Good at detecting patterns and features of images, audio, video, text, etc. Robust to translation, rotation, and scaling invariance. End-to-end training, no need for manual feature extraction. Can handle large amount of data and achieve high accuracy. Okay. So in this session, we have seen with the example pooling, padding, and different layers to build convnets, input layer, convolution layer, next activation layer, pooling layer, and another one is dense or fully connected layer, output layer. Thank you.